Welcome to one of the most massive underground construction sites ever built in history. Right now, thousands of engineers and heavy machinery systems are working relentlessly day and night, directly drilling through the entire solid rock structure at a depth of over 2,000 meters below the peaks of the Alps. They are facing the extreme compressive force of the Earth's crust to create a 57.5-kilometer underground railway. But that is just the number for the main tunnel tube. The total length of the underground network they actually have to excavate is up to 162 kilometers. And to do that, they have to remove 37 million tons of hard rock, a massive volume of material equivalent to building at least 6 Great Pyramids of Giza. This is the Mont base tunnel, the core megaproject directly connecting France and Italy. When completed, it will reset the entire transportation system of Europe. So how did the engineers do it? And what techniques were applied to build this longest tunnel project in the world? Let's find out right now. Before we start, don't forget to like and share this video. And now let's get started. To understand why France and Italy are spending tens of billions of euros digging deep into the mountain, we need to look at the physical limits of the current infrastructure. Every year, over 3 million heavy truck trips have to cross the Alps. This traffic volume has exceeded the design limit of the road system. At the same time, emissions from millions of internal combustion engines are breaking down the region's natural ecological structure. The only solution is to switch to railways. But traditional mountain railways face a core mechanical barrier: the slope. A steep slope generates a strong gravitational drag, limiting the payload of freight trains and forcing the use of expensive booster locomotives. To solve this problem, engineers have to construct a base tunnel. Instead of building uphill tracks, they drill a perfectly straight line right through the base of the mountain, creating an almost perfectly flat running surface for the trains. Thanks to this underground system will directly take 1 million truck trips off the roads every year. Freight trains will be able to pull heavier payloads without booster locomotives, while passenger trains can run at a speed of 220 kilometers per hour, cutting the Milan to Paris travel time from 7 hours down to 4 hours. But the technical price to pay is extreme depth. This tunnel route lies up to 2,000 meters deep below the peaks of the Alps. At that location, they have to face the direct compressive force of billions of tons of rock pressing down on the tunnel shell, and the heat from the mountain core baking the working environment up to 50 degrees Celsius. That is why heavy mechanical machines must be brought underground. To drill through the massive structure of the Alps, engineers cannot apply a single method for the entire 162-kilometer tunnel network. This underground system is designed with a 3-layer structure. The first layer is 2 parallel main tunnel tubes, each with a diameter of 10.4 meters. Each tube handles an independent direction of train travel, completely eliminating the risk of head-on collisions. The second layer, to ensure ventilation and evacuation, every 333 meters, engineers drill a cross passage connecting the 2 main tubes. There are a total of 204 such cross passages. The third layer is the access tunnel system. Engineers drill 4 large-scale sloping tunnels plunging straight from the surface down to the design depth. These access tunnels are the gateways to bring heavy equipment underground, allowing them to construct simultaneously at multiple different points, dividing the 57.5-kilometer tunnel route into multiple independent sections. And to punch through 80% of the project's hard rock structure, they deploy full-face tunnel boring machines, TBMs. First, because they cannot transport the massive 334-meter-long, 3,200-ton machine in one piece, the TBM is disassembled into individual modules at the factory. Heavy trucks carry these modules down through the access tunnel system. Right at the design depth underground, Engineers assemble the parts together to recreate a complete machine. After assembly, the TBM starts up. A hydraulic cylinder system presses against the completed tunnel shell behind it, creating thousands of tons of thrust to push the front rotating cutter head straight into the rock face. Under continuous pressure and rotating motion, dozens of alloy disc cutters bite directly into the rock face, shattering the solid rock structure. As soon as the rock is crushed, buckets mounted on the cutter head scoop up this crushed rock mass, dumping it into a central hopper. From here, a long internal conveyor belt system running along the machine's body continuously moves the rock to the back to transport it out of the tunnel. At the same time as the TBM moves forward, the newly exposed rock face immediately faces the risk of collapsing under the pressure of 2,000 meters of mountain rock above. The TBM automatically solves this problem with a massive hydraulic robot arm. This arm picks up precast concrete segments, each weighing between 4 and 8 tons, and assembles them into a closed, load-bearing ring pressed tightly against the tunnel wall. Finally, a pumping system injects grout to fill the gap between the concrete ring and the rock face, locking the permanent shell structure in place. However, this 3,200-ton machine has a physical weakness. It only works well in hard rock zones. In the 20% of the project length that passes through geological fault zones, where the rock is fractured and waterlogged, the mountain shell will squeeze and clamp down, causing the TBM to get completely stuck. That is when engineers have to pull the TBM out and switch to a mechanized manual method, the NATM method. First, multi-boom drill jumbos move close to the rock face, using a hydraulic drill system to punch a series of deep holes into the fractured rock mass, according to a pre-calculated mathematical pattern. Next, engineers pack explosives into these drill holes. To avoid collapsing the entire weakened mountain structure, the detonator system is set with millisecond delay intervals. The first blast breaks the central core, while subsequent blasts force the surrounding rock rim to collapse inward, carving out an underground space. After the blast, a high-capacity ventilation system immediately pushes all the dust and exhaust gas outside. Next, low-profile loaders move in, scooping up the entire volume of freshly broken rock and dumping it onto trucks to clear the site. As soon as the open rock face is exposed, the core reinforcement stage is triggered following a strict physical cycle. First of all, to prevent loose rock from falling, engineers use high-pressure hoses to immediately spray a thin layer of fresh concrete covering the rough rock surface. This membrane acts to instantly lock the tunnel face. After that, they use drill rigs to punch and insert long steel rock bolts deep into the mountain core, creating solid mechanical anchor points. At this point, a welded wire mesh system is brought in, fitted tightly against the tunnel profile, and hung directly on the bolt heads. Finally, the hoses continue to spray a second, thicker and denser layer of concrete, trapping the entire wire mesh in the middle to create an embedded, reinforced concrete shell. The physical nature of the NATM method is to allow this integrated shell to deform and shift by a small margin. This mechanism helps release some of the massive mechanical pressure inside the mountain block before they proceed to cast the permanent concrete shell. But digging the tunnel is only half the problem. The biggest question is, what makes this project special compared to other underground works in the world? The core difference does not lie in how they cut the rock face, but in how they handle the 37 million tons of freshly excavated material. In typical projects, this volume of crushed rock would be scooped onto hundreds of thousands of truck trips and hauled away to be dumped. But at Mont, using trucks would directly create massive congestion and emissions, completely destroying the project's original ecological protection goal. Instead, the engineers set up a closed-loop mechanical cycle right at the construction site. The rock, after being crushed by the TBM, will not touch the ground. It falls directly onto a continuous industrial conveyor belt network. This system is tens of kilometers long, running through auxiliary tunnels and bringing materials out at a 24/7 capacity. The conveyor belt system transfers the rock straight to large-scale material processing plants built right next to the tunnel entrance. Here, a screening system separates the rock by size. The rock blocks that meet physical hardness standards will be fed into smaller crushers. Their goal is to reuse more than 50% of this total 37 million tons of material. The crushed stone is mixed directly with cement and additives to produce fresh concrete right on site. This volume of concrete is then poured into molds to cast the very high-strength tunnel shell segments. Finally, these tunnel shell panels are transported back underground, supplied to the TBM for assembly. In physical terms, they are taking the very rock structure of the Alps to rebuild the permanent supporting shell for the tunnel. This is a circular production process that minimizes transport costs and completely eliminates industrial waste leaking into the outside environment. Once the final tunnel lining is secured, a new physical challenge arises. How can heavy freight and passenger trains hurtle at 220 kilometers per hour within a sealed underground space? Typically, railway tracks are laid on a ballast layer to dampen vibrations. However, in this 57-kilometer tunnel, the rules change. At high speeds, the train acts as a massive piston, compressing the air ahead into violent aerodynamic forces. This wind is powerful enough to displace ballast stones, causing them to strike electronic components and the train's undercarriage directly. Furthermore, maintaining such a ballast layer deep inside a mountain is a logistical nightmare in terms of cost. The engineer's solution? Eliminate ballast entirely in favor of slab track technology. The rail system is positioned directly on the tunnel floor, where laser surveying instruments scan and fine-tune its coordinates with absolute precision, down to the millimeter. Immediately after, self-compacting concrete is injected to lock the entire structure into a single monolithic block. The result is an ultra-rigid system that eliminates vibrations and flying debris, ensuring maximum physical safety for high-speed journeys across the Alps. The Mont base tunnel is not merely a path carved through a mountain. In technical terms, it is the most complex underground logistics machine humans have ever built to break the physical limits of nature. By applying giant mechanical systems and a circular recycling process right underground, engineers have found the answer to pull 1 million truck trips off the road every year. This project directly reshapes Europe's entire transport trade network, while putting an end to millions of internal combustion engines, destroying the Alps ecosystem. What do you think about the mountain carving techniques and the anti-collapse process of this mega project? Leave your analytical thoughts right down in the comments section. If you found this video provided useful technical knowledge, hit like, share, and subscribe to the channel to keep watching the most detailed mega project anatomy videos. Goodbye, and see you in the next project.